all your questions on the exam come from either discussion worksheet or come from your chapter end problems. So I don't want you to be surprised by anything. If you studied your textbook, you studied your worksheet, you should be doing fine. But the most important thing is, even if it is an open book exam, don't study during the exam. So if you read the question, you're like, I don't know what this question is talking about. It's much better you skip it and come back later than you just sit there and trying to go over your note and find a relevant concept or equation to use. Because you will run out of time if you do that. Okay, so those are the general suggestions. And your midterm exams covers from 3.4, when we talk about mixing of different inert ideal gases, all the way until the beginning of 6.2, which we talk about ideal gas and equilibrium and so on. All right, any questions on the administrative end for the midterm? Nope, we're really clear? Okay, sounds good. All right, so today's buffer lecture is pretty much focused on the first 2 weeks of your midterm exam. Means like it starts from the chapter 3.4 all the way to like 4.5, where we talk about thermodynamic thermodynamic relations. And things after 4.5 are actually pretty straightforward. They're just application of the thermodynamic tables and how to use the thermodynamic tables to calculate properties. So let's see how far I go, because I was preparing for my buffer lecture. I realized I probably won't be able to finish everything if I want to cover everything. So I want to just focus on the first half, because it's been a while and I want to refresh your memory on some of those topics. And again, those topics are not in my buffer lecture. It doesn't mean they're not on your midterm exam. Remember, the coverage of your midterm exam goes all the way to chapter 6.2, the equilibrium, but on the conceptual end. Okay, getting started. So right after midterm 1, the first lecture we have is to pick up where we left over, which is talking about entropy. So I want to use this as a nice example, because entropy change for mixing of ideal gases is one of the good examples that tells us more information about what exactly is entropy. What is the physical meaning of entropy? So it's like, if you're going to remember anything from this class, I hope you can at least have an understanding in what exactly is entropy. So let's get started. So in 3.4, remember we talked about the entropy change for mixing of ideal gases. So here's the setup. We're saying you have 2 gas chambers that are separated by a solid wall, adiabatic solid wall. Now, upon removing that solid wall, we have the irreversible mixing of the 2 ideal gases, and we end up having the final total number of mole equals to Na plus Nb, the final volume equals to Va plus Vb. That's a setup. We solved this problem using the definition of entropy from the second law of thermodynamics. So what we did is derive the delta S for this process by taking the integral of Q reversible over T. When doing that, we build a reversible pathway for this irreversible mixing to take place. Remember, the first thing we do is now imagine we expand both gas separately into the final volume, and then we mix it. We did an isothermal mixing of the 2 ideal gases. So if you don't remember that, go back to review your lecture note a little bit. With that in hand, we then used a combination of the first law of thermodynamics, du equals to dq plus dw, and your S equals to dq reversible over T, also your ideal gas law, PV equals nRT. So we used these relationships along with that reversible path that we built to end up having an expression for the irreversible mixing of your ideal gas. So this is one of the things like you need to know where to find that equation, you need to know how that equation comes from, and what derivation has been taking place. And now if we have a situation like that, how to apply this equation to solve for your entropy change. But nevertheless, if we look at this relationship that we solved for, the total delta S for this irreversible mixing of ideal gases only depends on the original composition, right? What is your original number of mole of your molecule A on the left-hand side, and what is your original number of mole of molecule B on the right-hand side? It doesn't matter what's the temperature, what is the pressure you're using. So how does that relate to the physical meaning of the entropy? So I want to take one more step. That's the next lecture after that first one. Well, that's still in the same lecture. And in that same lecture, we went over the physical meaning of entropy. So in this part, we gave the second law of thermodynamics a more easy to remember form, which means your delta S for the entire universe, or the delta S of an isolated system, if you consider the entire universe as an isolated system, can always increase or equal to 0. So delta S in an isolated system equals to 0 for all reversible processes, and delta S is larger than 0 for irreversible processes. So if you're working on the textbook problems, you'll figure out sometimes those problems have ambiguity terms. For example, it would say the delta S of a system of a reversible process must equal to 0. But because it didn't specify it in an isolated system, that is not true. So when working on those multiple choices or true and false problems, you want to keep your mind in focusing on all the terms, like reversible, irreversible, isolated, open or closed system, etc. Okay, so back to our question. Again, I want to emphasize what is the physical meaning of entropy. So the way to think about it is because our delta S can only increase until we reach that equilibrium. So on this picture, right, so that's the curve we went over, your entropy can only go up. So that means your entropy will maximize when that isolated system reaches the equilibrium. All right, so this is just a graphical representation of the second law of thermodynamics. And again, when reading it, we're saying the thermodynamic equilibrium of an isolated system is reached when the system's entropy is maximized. Or vice versa, when the isolated system's entropy is maximized, we say that system has reached the thermodynamic equilibrium in an isolated system. Now, let me take one step further to think about what exactly is the nature of your entropy. So we know entropy is maximized when we reach equilibrium. So what else is maximized when we reach equilibrium? And also think about what is the nature of the second law of thermodynamics. So I'm going to do a quick simulation with you and see if it starts to make more sense. So the simulation we're doing here is the same setup, right? On the left-hand side, let's start with 10 red particles. On the right, we have 10 blue particles. And I give those particles a random initial speed and let those particles to go whatever direction they like. I run that simulation for 10 steps. And well, again, this is, okay. So this is our initial state. All the red is on the left, all the blue is on the right. And I let it run for 10 steps, and that's our final state. And if we look at this figure, it's sort of random. It means you don't have a clear trend. Well, it sort of goes down, but it never go back to that 10-10 original state, but it has fluctuation. You can go up or go down because our movement is random. And this becomes more obvious if we're talking about, say, now instead of 10, I only have 2 particles. And I ask those 2 particles to go randomly in my boxes. And we end up having really random behavior, right? Your blue particle in this case, maybe it just want to stay on the right. It just fluctuates around 2 and 1. It never goes to 0. And what about we let that number of particles increase and we run that simulation with more and more particles? So I did that simulation on our Hoffman supercomputer with 500 red particles starting on the left, 500 blue particles on the right. I let it run for 150 steps. It's a much longer simulation. And this is what we have. Now, that's our step one, so it never hit that 500 point. We can see a very clear trend of decreasing until we reach that line, that bottom line, around 250. So it means like 250 red on the left, 250 red on the right, and 250 blue on the left, 250 blue on the right. So this part, we see the system is almost reached that equilibrium point. It's just fluctuating over that equilibrium point. Now, this is only 500 particles. Imagine we're not talking about like gas molecules, right? In this room, we have how many moles of like oxygen gases and how many number of molecules of oxygen gases. So with that huge number of molecules available in our room, then our second law of thermodynamics becomes a very obvious one. Like it's always, your system is always going to stable at its equilibrium state because that's the most probable state. All right. So there's actually a name for that. We call it Maxwell's demon. So that means you can imagine a demon now all of a sudden take all the oxygen in the room and put it in some corner and everyone suffocates, right? But it doesn't happen because that probability is too small, and thus there's a huge entropic penalty for that event to take place. So the nature of entropy is the probability. Right, and then we went over a derivation to give a more quantitative picture to link your entropy with probability. And here's conclusion again. By our simulation, we find out the equilibrium thermodynamic state of an isolated system is the most probable state. That's the highest probability state. And we went over a nice derivation. Just using basic probability theory and also the nature of calculus, we find out the logarithm function is the only suitable function to link your entropy and your probability. Where here, K is our Boltzmann constant, C is some random constant that we don't care, because typically we don't care about the absolute entropy of a state. We're always talking about the relative entropy. So this C will just cancel out in most of our chemical applications. And we went back to our original problem where you have the mixing, irreversible mixing of your ideal gases. And now we solve that problem using probability theory instead of the second law of thermodynamics, the dq over T. And we went over the derivation like this. Now we know the entropy equals to constant times ln P plus C. Right, so what we want to find is the entropy for the state 2, the equilibrium state, and to state 1, which is on the left-hand side. That's the probability state. You can just write out what they are. So on the right-hand side, that's the equilibrium state. So we know P2 will just almost equal to 1. So our equilibrium state is only infinitesimally smaller than 1. And on the left-hand side, so that is our probability theory to come to play. So if you imagine we have like NA amount of particle A, and we have NB amount of particle B, right? And let's just make our life simpler, but in reality, it may not be like 1, 1. So here we're just saying that initially the volume, the number of particle A and number of particle B is the same. It may not be the same for other applications. Now, in this case, then the probability of all particle A on the left-hand side is 1/2, because it's partially evenly divided, to the power of NA. And the probability of your NB on the right-hand side, that's 1/2 to the power of NB, right? And because NA is NB, because we manually set NA equals to NB here, now our P2 equals to 1/2 to NA, right? And we're plugging that number to our probability definition of entropy, and we did our calculation to find a final result. And then we also use this equation to do the same kind of analysis because we know the number of moles, we know it's mole fraction. We can do the same kind of analysis and compare those two together. Both of them are delta S. Both of them should have the exact same results. And using this relationship and derivation, we find out, okay, so the gas constant we've been using so far It's just the Avogadro number times a universal constant, which is a Boltzmann constant. All right, and Boltzmann constant is related deeply, it's at the heart of statistical mechanics that you will learn if you're taking 110B. All right, so this part is just refresh your memory again on entropy. That's one of the things I really, really hope you get from this class by taking thermodynamics, is entropy is probability. All right, and the second law of thermodynamics is a probability law. So if we live in a world where you only have like 2 or 3 particles, then they might do random movement. That's what Brownian movements are. If you have a particle just in the gas and it's going to move randomly. And that's why we have fluctuation taking place in our real life as well. Okay. It's not directly related to your exam, but I do think it's necessary. I give you a little bit more lecture on the nature of entropy. Any questions on that? We're clear? Okay, sounds good. And then we move on to chapter 4. So chapter 4 is one of those lectures that's really, really mathematically heavy. And it's really easy for you to get lost in all the mathematical functions. So hopefully I can give you another like review on what are the connections between these terms we went over. So at the beginning, we start by linking entropy to material equilibrium. So material equilibrium is a special type of equilibrium that's particularly interest to us chemists. Right? We care about how reactions taking place. We care about how your phase transfer is taking place. And in this case, again, we restated what we have. The thermodynamic equilibrium in an isolated system is reached when the system's entropy is maximized. So what we are saying here is imagine we have a closed system that is at thermal and mechanical equilibrium. And that closed system can allow material or phase change to take place. So that's why it's closed, it's not isolated. Otherwise, at equilibrium, it will be, it will be perfectly at equilibrium. So in this case, we're just saying, imagine we have a closed system at thermal and mechanical equilibrium that allows material or phase change to take place. So what we have is the derivative of entropy must be larger than or equal to dq over t. All right, so that this in here, dq is not a reversible heat transfer. It can be an irreversible heat transfer. And remember, our ds is dq reversible over t, and your dq reversible is always larger than dq over t, larger than or equal to. And using this relationship, we can write out like TdS is larger than dq. Your temperature in the Kelvin scale cannot be a negative one, so we can safely move that temperature to the left-hand side. And we also have du equals to dq plus dw in a closed system. And thus we have du smaller than TdS plus dw in this closed mechanical equilibrium system that can undergo material or phase change. So this part is really straightforward. We're just using what we know from the second law of thermodynamics and what we know about entropy and equilibrium to build the relationship of du and TdS and dw. Then we use this relationship to define Gibbs and Helmholtz free energy. So the reason we're defining Gibbs and Helmholtz free energy is not because we like these names. It's because we want to have a criteria to evaluate whether or not a system is at material equilibrium, right? So we chemists care about how your system is going to reach a material or equilibrium. So that's why we define the Gibbs and Helmholtz free energy. So this part is being derived. This equation is being derived using the same one. And from here, we have A equals to U minus TS. And similarly, we did derivation into this relationship that your enthalpy minus Ts must be smaller or equal to 0 at constant Tp value, and on here is constant Tb. And we thus defined Gibbs free energy, G equals to H minus Ts. We're not going to do the derivation together, but if you don't remember how that's being done, you can quickly go back and check it. We also went over the physical meaning of your Helmholtz free energy and Gibbs free energy. So the Helmholtz free energy, we're saying the work done by the system is always smaller than or equal to negative delta A. So calculating delta A tells you how much work your system can do, how much total work your system can do. And for delta G, what we did is we went over that derivation and say your quantity of negative delta G gives you the maximized possible non-PV work that your system can do. And typically non-PV work is what we chemists care about, like electric work, or in biological reactions, you have other types of work that's not like expanding or contracting. So for this part, you will have some calculation. We went over questions like doing calculation to calculate delta A and delta G using their definition. But I want to do a quick example with you, like a true and false problem here. So this one is your example 4.1. So basically, let's read it together. Quantity U, H, A, and G all have the same dimension. So if you think about it, all four of these terms, they're all forms of energy. You can like add or subtract them. So this one must be true. All right, so when they're asking for whether or not they have the same dimension, the other way to think about this, what are the unit of these state functions or properties? Next up, the relation delta G equals to delta H minus T delta S is valid for all processes. So whenever they say all processes, you want to put a question mark there and think about it. So from the definition here, we have G is by definition H minus Ts. So if we just using calculus, you write out dg equals to dH minus TdS minus SDT. And this is obviously, if you take the integral, it's not always going to give you this kind of integral, unless we're talking about a constant temperature process. So the take-home message is whenever you see it says like all processes, just think a little bit more carefully before you put down a true for that question. All right, C, G equals to A plus V. So this one is actually true. If you think about the definition of G, so G equals to H minus Ts. We also need A, so A is defined as U minus Ts, and H equals to U plus PV, and so G equals to, well, U plus PV minus Ts. So H equals to U plus PV, and here's our U plus PV, and minus Ts for our G. And A equals to U minus Ts, so this gives you A plus PV, and this one is true. Next one. For every closed system in thermal and mechanical equilibrium and capable of only PV work, the state function G is minimized when material equilibrium is reached. It's really tempting to say true to this statement, but if you think about our definition before, we went over here, there's a requirement for constant Tp. So if we want to use that statement, we must specify constant Tp, and thus that is not true. So if you encounter this kind of statement, it's better if you go back to that equation and check what exactly is the condition required for that statement to be true. But you need to be very familiar with the material so you know which equation you're going to. Okay, and then we have E here. The Gibbs energy of 12 grams of ice at 0 degrees Celsius and 1 atm is less than the Gibbs energy of 12 grams of liquid water at 0 degree and 1 atm. So this one is actually tricky. Now it's saying the Gibbs energy is different. It's tempting. You start to think about, okay, delta H and entropy and start doing calculation. But the reality is pretty straightforward. Now your normal melting point for ice is 0 degrees Celsius. So at 0 degrees Celsius, your ice and water are in equilibrium with each other. Right, and in this entire universe, when they're in the equilibrium with each other, your total energy change, the total Gibbs free energy is not changing. And it's also specified the constant Tp we're looking for. So this one is false because they're at equilibrium. The delta G is 0, so their Gibbs free energy must equal to each other. And the last one becomes more straightforward. That's in the Gibbs equation or in the definition of those terms, you find these are all the same kind of dimension because you can add them or subtract them together. So that one is true. All right, so these are multiple choices, but you can easily imagine now, instead of multiple choice, we have a multiple choice. Instead of true and false, we have a multiple choice question. Now you have like 4 here and say like, maybe not that, but one of them is have a different dimension and select which one is it. So this kind of question is more conceptual. It shouldn't take you any time. You should like read it and you know the answer. But you need to be very familiar with the material to get them right. Okay? Any questions? Nope. Okay. I got this one wrong when I'm working on it because I was like, that looks pretty legit. And I forgot the constant TP relations. So these are the questions that tend to trick people if you don't read carefully. Yes?
Can you explain D just one more time, please?
Oh, this one just say, and you need to be constant temperature and pressure for the statement to hold true.
But is that,
This one?
is that not what it's saying?
It didn't say constant TP. So for every closed system in thermal and mechanical equilibrium and capable of only PV work, the state function is minimized when material equilibrium is reached. It didn't specify constant TP. I got that one wrong too. I know. Well, at equilibrium doesn't tell you anything about, well, pressure and volume or something. Okay. Next up. And then we get into the world of thermodynamic relations. So this is the section that people can easily get really lost behind all the math. And here, we're gonna do a little bit of math together, but I just want to emphasize again why we care about thermodynamic relations and how are we using them. So in this case, we start from our basic equations. That's our starting point. Again, if you have anything on your cheat sheet, you want to have these 6 equations on your cheat sheet. They're just by definition true. And from there, we did a quick derivation to find out this kind of relationships, like what is the derivative of your state functions, U, H, A, and G. So these are the 4 types of energies we take consideration in thermodynamics. So the way to do it is we start from du equals to TdS minus PdV. And for example, if we're talking about A, we'll just say like, hey, dA equals to du minus TdS minus SDT. And here du equals to TdS minus PdV. And that minus TdS minus SDT. Well, some of the term cancel out. We get negative PdV minus SDT. It is okay if you just use it directly, but the derivation itself is not hard. It's just plugging numbers. And by doing that for all the state functions, you get an expression of the derivative of these state functions. Yeah?
Should we know how to derive the volume dependence question?
Yes, we're getting there. All right, so it's sort of built up. We start from the fundamental 6 equations. That's a definition. And then we take the derivative of these equations and also their definitions to get into some of these derivative expression. Yeah.
So just to kind of clarify, if you ask us any question related to derivations, would we have to start
No, unless I specify, like you have to start somewhere. Otherwise, you can start wherever you like.
Okay.
But you can't say, because the textbook says it must be true. That's not valid.
Okay, fair enough.
So this one is we are just taking the derivative to get some information here. And also related to this part. Now, for example, if you're asked to calculate for the Helmholtz free energy, the way you can think about it, one of the approach is taking the integral on both ends, like negative PDV minus SDT. Right, so if you know how your entropy is related to temperature, how your pressure is related to volume, you have a way to solve for that integral. So that's why we care about their derivatives so far. And with that, we have an example to use the Gibbs equation to review the nature of our state functions. So what do I mean? So let's take this one as an example. So that's the thermodynamic, well, that's the expression we get from thermodynamic by using the definition of these state functions. We know that our enthalpy is a function of entropy and pressure, right? So you can also write dH using the total differential of entropy and pressure. So we have the partial derivative of H over S at constant P ds plus dH over P at constant S dP. And in here, we end up having, well, T equals to partial derivative of H over S at P. And here V equals to partial derivative of H over P at constant entropy. And when we say the nature of the state functions, for example, temperature, as a matter of fact, temperature just is a property telling you how your enthalpy is changing with respect to entropy at constant pressure. And in this part, again, you can write it down and use it however you like. But when you're looking at a derivation, in there you have like temperature and volume, you're sort of stuck. You might want to come back and see how those properties connect to a partial derivative. Okay. And then we derived Maxwell relations using the Euler's reciprocity relations. So this part is pure calculus. It's not hard. It's just saying like if you have a function that's dependent on x and y, and m and n are the two partial derivatives we care about, then you using the chain rule. I think this is the real chain rule. I've been using chain rule for different things. When you have partial derivatives taking different orders here, and these will be the same to each other. So that's just math and calculus. And we applied the Euler's reciprocity relations into all our Gibbs equations to get relationship between different partial derivatives. So if we use our dg one as an example, let's say dg equals to negative s dt plus v dp. So here s, that's our m, v is our n. So using this relationship here, you can easily write negative delta S. So S is our M here, P at constant T equals to partial derivative of N, wait, that's V, over T at constant P. So this set of Maxwell relations is 4 sets of partial derivatives equal to each other. So if you read that Maxwell relations, you'll find they link your temperature, volume, pressure, and entropy. So whenever you're stuck with a derivation that relates like temperature, volume, pressure, and entropy, you might want to go back to your Maxwell relations and check if there's a same kind of partial derivative you can use. Now, the most important thing we use Maxwell relations is to make sure we have a way to measure the change of your state functions, especially entropy, using other relations like T, B, and P experimentally. Okay, and then we come to the point, is how do we derive dependence of state functions? Because in order to solve for what those state functions are, you need to have something that's experimentally measurable. So we have a set of relations that do make sure you know how they come from. We can do one derivation here really quick. So in here, in our right-hand side, we have alpha. So obviously, let's write out the definition of alpha just as a handy tool. That equals to 1 over v of dv over dt at constant p. Or you can write alpha v equals to dv over dt at constant p. So there are lots of different ways you can solve this equation. You can start from the right-hand side and derive for the left, or you can start from the left-hand side to derive for the right. I don't care how you get it, as long as you find out that derivation is true. I don't care what path you take. So in this case, we have dh over dp at constant t, and that gives you the derivative of g plus ts. So this comes from the definition of your g equals to h minus ts over dp at constant t. You write it out using calculus. You have dg over dp at constant t. And at constant t, you can put the t out. So we have t delta s dp over t. All right. And some of the things we know, for example, go back to what we have here. So in this case, now we look at the Gibbs free energy dependence on pressure, and you can check what that is. Let's see. I don't have it here, but it's one of these relationships that if you do the derivation, you can find this just equals to V. And on here, the ds term, using the Maxwell relationships, we know that ds over dp at constant t equals to negative dv over dt at constant p. And now your dv over dt, that's just your alpha v. So that's minus t v alpha. That's how you get it. All right. So the next question becomes, why do we care about all these dependents? Like what exactly we're doing here by doing all these derivations? So in our next step, which I believe is in a different lecture, that's a little bit unfortunate, is we actually use what we derive to calculate changes in state function. So if we use ds as an example, so you write out its partial derivative ds dp over t dp plus ds dt over p dt. Now finding out the dependence of your entropy on pressure and temperature gives you a direct way to set up this integral. So you can try it yourself. So this one is our negative alpha v we just discussed. Your partial derivative of your s over t at constant p, that's your cp over t. That derivation is also available in your lecture notes. So by working out how your entropy or your Gibbs free energy or your enthalpy or your Holmes free energy dependent on these experimentally measurable coefficient or terms gives you a way to solve for that derivative. So if we write out the s equals to negative alpha v dp plus cp over t dt. And you can set up that calculation to be like delta s equals to the integral of p1, p2, alpha v dp plus t1, t2, cp over t dt. And there are things we know, right? Alpha is something you can measure, or we can give you as a constant. I mean, volume, if you're solving volume VdP, as long as we know the equation of state that tells you the relationship between volume, pressure, and number of moles, you have a way to solve for that integral. Cp, the heat capacity, is also something you can measure. We also went over later on, you can express that as a polynomial, like Cp equals to like A plus Bt plus Ct squared, etc., etc. Or it can be just a constant, depending on the setup. But there is a way we can solve for that integral. All right, so everything in here are experimentally measurable, or experimentally we can determine it. Okay, and the same applies to enthalpy. So we have delta H, or dH equals to Cp dt minus TV alpha plus V dP. So in here, just this first term, that's your dH over dt at constant P. And this term, that's your dH over dP at constant T. Now the derivation we went over in class, or you can try it yourself, but these are, the whole point we're solving for those like pressure dependence of enthalpy or pressure dependence, temperature dependence of enthalpy is because we want to set up that integral so we can solve for the change of state functions in every situation. Okay, I hope now that link is a little bit stronger, because before it feels like it's just two different parts. As you did all the derivation, you don't know what's that for. So these are what we're looking for. We're using what we derived to solve for a specific quantity. Now, this example is a very good example we went over in class together. So it gives you an equation of state and tells you what are those terms here and asks you to solve for an expression for your delta HM and delta SM for a change of state for this gas. So this one is important because, first of all, this one is general, right? We don't have any number in there. You can easily imagine now, instead of having P1, T1, P2, T2, we give you some number so you can solve for an actual number. 2, this one is a example that it's talking about one of the equation of state. You can replace this equation of state with other forms of equation of state and get a different kind of result. So if you don't remember what this part of the derivation is, I highly recommend you go back and review this section. Okay. Any questions? Nope. All right. And I'm running out of lecture notes on my buffer lecture, but we can quickly go over some of the things we discussed in class. So that's the 4.32, that's where we left over. I highly recommend you go back and see, right, first of all, how do you solve for alpha coming from this representation? And we did that practice for our first midterm. That's why we care about solving for alpha and chi for those complicated equation of state. I'm not saying you're going to do that again, but it's just saying like that's why we're doing that. That's why you're needed to do that. And you can solve for delta H, delta S for the given processes. Yeah. And from there, we went on to start talking about chemical potential. So this part will be directly linked to our equilibrium discussion that you will need after the midterm 2. So this part, we defined chemical potential by doing all these types of derivations. We went over and say, if we are talking about a system that is not at equilibrium, we have this chemical potential to take consideration about how material equilibrium is gonna take place, which direction that equilibrium is gonna move. So this part is lots of derivation, and we end up going to we end up talking about the phase equilibrium here by say like what exactly is chemical potential. And what we're saying is chemical potential tells you what direction your equilibrium is flowing in different phases, like temperature between different like temperature for your hot and cold systems where the heat flows. So that's our lecture 4. We have our reaction equilibrium. So this part is pretty straightforward. You have a reaction. We now generalize that reaction to have your stoichiometric coefficient, negative for reactant, positive for product. And we define our extent of reaction C. So that's the delta N equals to your coefficient times the extent of reaction, or the proportionality of reactions. We did some examples together, but this part should feel relatively straightforward for you. Like we have the initial number of mole of your reactant and product. We have the final number of mole of one of your reactant or product, and you can solve for the change and solve for the extent of reaction, solve for what are the properties of other chemicals. Okay? And yeah, so this part is end of our lecture 12, lecture 13. So for our entire chapter 5, let's just put it this way. Entire chapter, yes?
Sorry to interrupt. I was just curious if, like, for the chemical potential stuff, you'd want us to, would the problems be more calculation-based or more conceptual?
Both. Again, if you're worried about conceptual problems, I highly recommend you look at the chapter end problems, especially the trend force problems in there. All right. And next up is number 13. So in chapter 5, so in the rest of chapter 5, I'm just going to summarize it in like a few sentences. What we do is we're talking about a thermodynamic table. So when we look at a thermodynamic table, that's what it looks like, right? So you want to know, for example, how that heat of formation is being measured. So we spend a lot of time talking about different steps and also calorimetries for you to measure the heat of formation. So I don't want you to treat this table as something like exist, right? So there are physical chemists doing lots of experiments to put numbers in that table, and that's how those experiments are being done. And then know how to use the table to find out the reaction, the heat of reaction, using the heat of formation from the thermodynamic table. Likewise, the same applies to our conventional molar entropy, right? First of all, what is conventional molar entropy? So that's the relative entropy compared to your species at 0K, which is by our arbitrary assignment. And the third law of thermodynamics, we say that at 0K, we assign your absolute entropy to be 0. And then we went over that really long step of derivation. If you remember, we have like about 11 steps there, or 9 steps, that we went over the calculation of the molar entropy of sulfur dioxide, and know that how to use the area under the curve to approximate for that integral. So let's see here. That's right, so in this case, when we're talking about the delta S change for between your temperature 15K to your melting point, we approximate your entropy change by looking at the area below the curve here. And the reason we can estimate it using the area is because of that derivation. So this part should be pretty straightforward. It's again, we went over this to tell you how people get to those tabulated data, and then how to use those tabulated data to find entropy of the reaction, and consequently Gibbs free energy of the reaction. Any questions? Chapter 5, I think it's really straightforward. It's conceptually straightforward. I'm not saying the calculation is easy, but conceptually, chapter 4 is way more challenging comparing to chapter 5. And as a final conclusion remark, 50% of your grades are multiple choice and true and false. And that means you want to read those questions carefully and get familiar with those terms. Okay, any other questions? No? All right, I'll see you next Wednesday or after Thanksgiving.